Hi, everyone. Thanks for joining from wherever you are in the world. It's great to be here. I'm Joshua Yu, founder of GraphWay, and I work on knowledge graphs and GraphRAG systems, particularly how to make them accurate, consistent, and reliable over time. Most GraphRAG discussions today start with a familiar question: how do we turn text into a knowledge graph? But in the real-world systems, the reality is the quality of generated responses degrades with the growth of knowledge graph over time. The real and the bigger challenge I've been seeing is not GraphRAG itself. It's that we often treat knowledge graph as a static artifact instead of a system that needs to evolve. In this talk, I want to shift the focus on what happens after the extraction, how we ensure knowledge graph quality, how we maintain consistency, and how we evolve the graph along the way. So let's start with the problem. GraphRAG is attractive because it adds structure and a multi-hop context to generative AI. But many GraphRAG systems quietly assume the knowledge graph is already correct, clean, and connected. In production, when graphs are larger, complex, and growing rapidly, the assumption breaks fast. So the real challenge is not just graph construction, it's graph maintenance and graph evolution. Let's make this more concrete by looking at some of the most common failure modes we see in real knowledge graphs. First, duplicates. The same real-world entity shows up under multiple names, abbreviations, full names, slight variations, so on and so forth. To a human, they're obviously the same. To the graph, they're completely different nodes. Then we have the coreference drift, things like it, this program, or the association. If we don't resolve those properly, we lose continuity across the graph. Next, composite entities. Sometimes extraction bundles multiple concepts into one node, like anxiety and depression. That looks fun at first, but it breaks reasoning and limits how we can traverse the graph. Then there are contradictions. Different documents, or even the same document over time, may assert conflicting facts. If a graph doesn't capture or reconcile that, we end up with silent inconsistency. We also see fragmentation. Instead of one connected graph, we get many disconnected islands. That severely limits multi-hop retrieval, which GraphRAG depends on. And finally, weak provenance. Fact exists, but we can't clearly trace them back to source evidence. That makes it hard to trust the output and hard to debug when things go wrong. Individually, this issue seems manageable, but together they compound, and this is where GraphRAG starts to quietly fail. My core claim is simple. GraphRAG should be treated as a life cycle discipline. We need a structured methodology for how knowledge is modeled, enriched, evaluated, and evolved. In many cases, fixing the graph yields more value than swapping one LLM for another. Let me introduce the generative knowledge graph lifecycle. Instead of treating a knowledge graph as something we built once, we treat it as a system that evolves over time. We start with discovery and modeling, understanding the domain, and deciding the structure of the graph. Then extracting and constructing the initial graph from text. But the real value comes after that. In enrichment, we clean and structure the graph, resolving duplicates, coreferences, and abstraction. And importantly, this is also where governance begins. We define what is allowed in the graph, how entities should be represented, and what constraints we want to enforce. For evaluation, it needs to be across the whole life cycle and measures both structure and semantic quality. This life cycle turns a classic graph into a living system, and that's what enables adaptive GraphRAG. By adaptive GraphRAG, I mean a GraphRAG approach where the graph is not static. It is continuously assessed and improved using structural signals, semantic checks, and the downstream retrieval outcomes. It is about adaptive graph quality, adaptive consistency, and adaptive evolution. So what does this look like operationally? There is an enrichment loop exists in this adaptive GraphRAG, which involves several steps or tasks. Split, phrase like anxiety and depression should not always be one node. Abstract, specific instances can roll up into higher level concepts. Resolve, pronouns and indirect references need to be grounded. Normalize, consistent naming reduces graph drift. Link evidence, every claim should remain traceable. And the cluster duplicates. Graph algorithms can help with identify consolidated candidates. This is where the KG starts to become retrieval ready rather than just extraction complete, when quality becomes a first-class concern. Once we start talking about graph quality, the next question is, how do we actually measure it? Because saying this graph looks better is not enough. We need a graph native matrix that tells us whether the structure is improving over time or not. One important signal is giant component growth. As the graph matures, more nodes should become connected into a single large component. If the graph stays fragmented, it limits multi-hop reasoning and retrieval. The closely related is the number of isolated subgraphs. Too many disconnected islands usually indicate missing links, unresolved entities, or poor normalization. Then we have duplicate density. How many nodes are actually representing the same level of the real-world concept? If this is high, retrieval becomes inconsistent and brittle, which leads to alias to canonical consolidation. Over time, we want more mentions and variations to converge onto stable canonical entities. That's a sign the graph is becoming more coherent. Another key metric is evidence coverage. When we convert text into knowledge graph, how many facts in the graph are actually grounded in source material? This directly affects trust, explainability, and debugging. And then finally, structural stability across ingestion cycles. As new data comes in, is the graph becoming more consistent, or are we introducing more fragmentation and noise? So the key idea here is graph quality is not just semantic, it's structure. And if we want adaptive GraphRAG, we need to track these signals and use them to guide how the graph evolves over time. Knowledge graphs in the age of LLMs are no longer just manually designed or statically constructed. They are partly generated, partly structured, and continuously refined. And I call it generative knowledge modeling, or GNKM in short. GNKM is not a single technique. It's a combination of stages that work together to turn unstructured data into reliable, evolving knowledge. We started with knowledge graph. We started with the document graph. This preserves the original structure of the source: documents, sections, chunks, and sentences. This is our foundation for context and evidence. On top of that, we build the entity relation graph, entities, relationships, and claims extracted from the text. This is what most people think of as the knowledge graph. Then we introduce the cluster graph, where we aggregate and summarize information, giving us a more global view of the content of the knowledge in the graph. Ontology graph can be added before and or after, which define concepts, terminologies, and class hierarchies. This is where meaning becomes stable and consistent. Crucially, we maintain cross-stage links, which connects everything back to its source with full provenance, so nothing loses context. And finally, there is an operational layer where query time state is created during serving, supporting time-variant, personalized context for GraphRAG and agent workflows. So instead of a single graph, we have a system of connected graphs from raw documents to structured facts to global understanding to runtime intelligence. That's the essence of the GenKM. In the implementation view of adaptive GraphRAG, Neo4j stores not just entities and relations, but also evidence and concept layers, together with the runtime operational intelligence. For example, for a specific question, what are the founding or grounded chunks from the original document have been retrieved and ranked? And what is the final generation of the responses? Cypher handles graph traversals, transformations, and the repair workflows. The Graph Data Science GDS helps us inspect structure and detect likely consolidation opportunities. And LLMs are used as controlled assistants for tasks that are hard to do symbolically. The key is not blindly trusting LLMs. The key is replacing them. The key is placing them inside a graph-centered lifecycle with traceability and evaluation. Let me briefly introduce the document graph, because it is one of the most overlooked parts of GraphRAG architecture. A document graph preserves the structure of the original source material, documents, sections, chunks, and sometimes sentences, along with their hierarchy and sequence. This matters because meaning is often shaped by context, not just isolated text spans. Especially for legal documents and instruction manuals, it is crucial to keep the exact order and complete structure. So looking at an example here on the screen, we see the purple nodes are actually representing the chunks of the original documents, separated by their natural paragraph or sentence. They come from the purple nodes, which represent the section in the document, for example, chapter, subchapter, and sub-subchapter, so on and so forth. And the cyan node represents the original document. So entities, the claims mentioned involved in each chunk are represented in the green, as the green nodes here. And within claims, there are brown nodes representing the entities mentioned. So by modeling document structure explicitly, we can trace every extracted entity or claim back to its source location. That gives us provenance, explainability, and a much better evidence layer for GraphRAG. One key piece that makes adaptive GraphRAG work is the ontology graph. Instead of treating extracted entities as the final truth, we anchor them to a canonical concept. Why is that? Extraction gives us surface mentions. The ontology graph defines meaning. The canonical layer connects the two. Ontology reduces duplicate entities, stabilizes naming, supports abstraction, improves retrieval consistency, and allows evolution without breaking queries. The ontology graph evolves more slowly than extracted entities, so they are more stable. It becomes the semantic backbone that keeps the knowledge graph consistent over time. In Neo4j, we typically model this as a concept layer, which relationships like instance of between the entity and a terminology, broader or narrower between terminologies, defined as has acronym or domain-specific types. Entity extracted from the text are then linked to those ontology nodes, which give them very strictly defined, non-ambiguous definition or meaning for specific domain. Generative knowledge modeling also defines the missing how, which are reusable transformations that create, refine, connect, and serve knowledge across stages in an AI native pipeline. We call them operators. Operators are the actions we apply to the graph, things like deduplication, convolutioning the meaning, embedding, prediction, and aggregation, to name some. They combine LLM with graph operations to continuously refine the graph as new data arrives. And because they are repeatable and auditable, they give us a practical way to manage knowledge graph quality over time. Here are some commonly used operators during the enrichment or adaptive GraphRAG systems, with the inputs, outputs, and the usage mentioned on the slide, which I will cover with more details in the following slides. Oops. Let's take a look at operator dedupe. The goal here is very straightforward and simple. Identify and resolve entities that actually represent the same real-world concept. We started with a batch of newly imported entities, for example, from a recent ingestion cycle. For each entity in that batch, we look for similar candidates in the existing graph. In Neo4j, we can do this efficiently using vector index, where we query for nearby nodes in embedding space. So instead of comparing every entity with every other entity, we narrow it down to a small set of likely matches. Then for each entity, for each candidate neighbor, we compare normalized names or the canonical forms, which removes the plural format, any uppercase, lowercase to be standardized as well for simple match. If they match, we can keep both nodes and treat them as linked aliases through same as relationships. Or if we are confident enough, we can merge them into a single canonical entity using something like APOC refactor merge nodes. Metadata like confidence, method, and batch ID is also stored, so the decision is traceable and auditable. To summarize, this operator is enforcing entity consistency, is capturing lineage and decisions, and is turning a noisy graph into a more coherent one. And importantly, it is not a one-time step. We run this continuously as new data arrives, so the graph becomes more consistent over time. Another operator, prediction, in short PRED, discovers implicit relationships between entities that are semantically related but not explicitly connected in the graph. This is how it works for entities created in a batch. First, it retrieves semantically similar entities already in the knowledge graph using the vector index. Then, for each entity pair, it computes a composite score from two other independent signals. One is the Adamic ADA score. Do they share rare structural neighbors in the graph and common concepts? Do they belong to the same ontology classifications or linked to the same terminologies? Different from the Jakarta similarity, Academic ADA measures how structurally close two nodes are by counting their shared neighbors, but giving more weight to shared neighbors that are rare, which means has a low degree, than to hubs, which means having a high degree. So when the score, the final score, the composite score exceeds a predefined threshold, a related relationship is created. AGGR aggregation organizes the flat entity set into a two-level hierarchy by identifying the most prominent concepts as cores and attaching everything else beneath them. The two steps involved. The first one is the core marking on the global graph. The top K entities, by counting mentions relationships across the entire graph, are promoted to the core row. These represent the most frequently discussed concept in the source documents, which are the anchors of the knowledge base. Then the second step for each delta ingestion or batch, which is the child attachment. Every non-core entity finds its nearest core by vector similarity and gets attached via a has-child edge. The result is a navigable summary layer. Start at a core concept, traverse has-child to explore related specific subchildren. This gives the agent a structured entry point into the graph rather than a flat, undifferentiated set of entities. Let me make this more concrete with a quick case study. This is a diabetes companion system designed to provide safe, contextual, and evidence-grounded support for users. What's interesting here is that it combines two things we've been discussing, GraphRAG and agentic architecture. The GraphRAG inside ensures responses are not just generated from text embeddings, but anchored in a graph that preserves meaning and context. On the agent side, we introduce controlled reasoning and actions based on domain semantics. The agent can resolve terms, check for ambiguity, follow relationships in the graph, and decide when to provide an answer, ask for clarification, or escalate. This is especially important in a domain like healthcare, where accuracy and safety really matter. The entire system is deployed on Neo4j Aura, using both the Aura database and the agent layer, so there's no infrastructure setup required at all. Conscious of time, I won't be able to demo it today, so I put the links to GitHub repo and a blog post for your references. Feel free to have a play yourself and share with me what you think. When combining a well-structured, evolving knowledge graph with agentic reasoning, you get systems that are not only more capable, but also more grounded, explainable, and reliable. I'd like to conclude my presentation with one phrase: fidelity in, quality out. What is not preserved in meaning cannot be recovered in reasoning. If a GraphRAG is going to move from demos production, we need to move beyond extraction and adopt a structured methodology for knowledge because knowledge is modeled, evaluated, and evolved over time. That's what I've tried today to outline with Adaptive GraphRAG, part of the generative knowledge graph lifecycle, an approach where the graph is not static, but continuously enriched, measured, and refined. At the Neo4j Graph Database, GDS, the Graph Data Science, and Aura provide practical features and ready-to-use operators to build exactly that. And this is my talk. Thank you.